Let's take a quick tour of some basic parent functions. We'll explore their shapes, y-intercepts, and what makes them unique. First up, the linear function. This is the classic y = x equation. The graph is a straight line that passes through the origin. It has a y-intercept at 0, and the domain and range are both all real numbers. What makes it special? It's the simplest, and it shows a constant rate of change. Next, the quadratic function, y = x squared. The graph forms a smooth U-shape called a parabola. It also has a y-intercept at 0, and its domain is all real numbers. The range, however, is y greater than or equal to 0. The quadratic function is special because it's the first to bend over, unlike the flat line of the linear function. Now the cubic function, y = x cubed. Its graph looks like a smooth S-curve that passes through the origin. Good googly moogly. Both domain and range are all real numbers. The cubic function is unique because it can curve in both directions, unlike quadratics which only curve up or down. Moving on to the absolute value equation. Y = the absolute value of x. The graph makes a sharp V shape with a y-intercept at 0. The domain is all real numbers, but the range is y greater than or equal to 0. What makes it stand out? Instead of going in a straight line, it hits the spread eagle. It's the first function with a sharp corner instead of a smooth curve. Here's the exponential function, y = 2 to the x. Its graph starts near the x-axis and rapidly increases as x gets bigger. The y-intercept is at 1, and the domain is all real numbers. The range is y greater than 0. It's special because the rate of change increases exponentially, making it grow faster than any polynomial. Finally, the square root function, y = the square root of x. The graph starts at the origin and curves upwards and to the right. You know what else curves upwards and to the right? The domain is x is greater than or equal to 0, and the range is y is greater than or equal to 0. It's unique because it only exists for non-negative x values, unlike the other functions. Each of these parent functions has its own unique graph and properties. Now that you've seen their basic shapes and characteristics, you can explore them further on your own.